Good afternoon, class. In today's video, what I'd like to do is to talk about voltage. And in the last video, when I talked about electric potential, what I did mention was about an analogy about how gravitational potential energy and how electric potential can work together and give you somewhat of an understanding. And I stand by that. However, what I did want to do is also give you another analogy, or maybe a metaphor would be better. Apologies to all the English teachers out there if I used the words wrong on that one. So in this case, what I'm going to do in this video is I'm going to go over voltage again, just to make sure you have the equations down, and then I'm going to go over an analogy to again help maybe solidify in your mind what voltage is, what it looks like, and how to utilize it in in your thinking when you're going about solving the equations and even just visualizing what's happening in the world of electricity. One thing I do want to note, no matter what happens, no matter if you like the analogy that I wrote in blue or the one in red, whichever one works for you, works for you. These are analogies. These are not meant to at all be the defining measure of how you think about about the material, or even any of the concepts that we're going over. If it helps, it helps. If it doesn't, figure out another one, or use one, use the other, use both. Don't use any of them and come up with your own analogy. All of those are valid because they're not the concept. They are just the way to help you remember it. The thing you cannot argue because it is proved by experiment are these equations, and and that's it. Those are the ones that you need to understand. This is fact. I'm sorry, let me try this again. This is fact, and this cannot be argued because it is found via experiment, versus these are analogies that are given solely to help you visualize the process. So if analogies need to be thrown out, they can be thrown out without any consequence. The equations, on the other hand, cannot be thrown out without dire consequences to physics. So just keep that in mind as we're going through this. These are important. These are helpful, but not as important. Okay, so let's go into it. What does voltage look like? It is an electric. One of the equations is kq over r, where it is electric field over time over a distance. So it would be kind of like in my gravitational potential energy example. You could have a high voltage or a low voltage, and it is the motion between the two that is the problem. And the real danger to electricity and voltage in particular is that you don't know necessarily, there are no obvious signs that say, oh, you're at a high voltage, and if you do this wrong thing, which is very easy to do, like touch this thing, step in this place, you're going to get a current going through your body that can kill you. So you have to, that's where you have to be careful, and it's not intuitive because it's not always clear when you're at a high voltage and when you're at the low voltage. So that's one way to think about it. The other way to think about it is using what's called Ohm's law. And in Ohm's law, voltage is V, current is I, and resistance is R. So V equals IR is Ohm's law, which, by the way, should look a little familiar. It should look a little bit like F equals MA, P equals MV, all of those different equations that we've dealt with so far. This should start to look and feel a little bit familiar as we've gone through the course of physics. Now, the analogy that I'd like to make to help you remember Ohm's law is one of a lake. So you have one lake with a river connecting it to another lake. So I named this lake high voltage and lake low voltage, with the river current flowing between the two. That's where these little lines are for. These circles right over here, and hopefully you can see that, are rocks in the river, and they represent resistance. So, and of course, because like I said in the other videos, my artistic skills are not the best, and I fully recognize that. So that's why I drew them. I even have little splashes of water coming off of this river. But if you can't tell that because my drawings are just that bad, then don't worry about it. I am not offended. I'm the first one to recognize that. So that's why, and physicists in general come from all walks of life and all artistic abilities. So all of us have struggled with this ability to draw something and that everyone will understand. So the way that we did it was, again, stick figures, because everyone understands what a stick figure is. Also, even if you don't understand what these circles represent, if you put words help. That means you're able to look at this and say, this points to, this thing that it's pointing to must mean those are the rocks in the river, and they represent resistance. So the way that you can think of it, like so this is the analogy that hopefully it works for you in terms of visualizing it, because really what it is there's an electric potential that is built usually by a battery, and so you'll have a battery that raises the circuit to a higher voltage, and that voltage then gets carried by the current. All the electrons at that high voltage get carried by the current through the wire, and then the current gets carried through the wire, and then it encounters resistance as it's going through that. And in the same way that when rocks, or when you have rapids in a river and you can get like splashing, some of the water can splash out, and all of that stuff. The same way, that's what rocks in the river will do. That's what resistance actually is. Because, and if you'll notice, and you can actually notice this too, especially if you're watching this video on like your cell phone, as you watch it, you might notice that your cell phone's getting hot. And that's because the energy and the electricity that's flowing through your cell phone is actually heating up the circuits in the cell phone itself. You can do this even with a computer. I mean, that's why most computers, you'll hear that little hissing sound coming from it, because there's a fan to actually cool the circuits that are inside the computer, so that it doesn't overheat and just shut down. So any electronic device actually has that, where it will actually start to get hot as you use it, because as the current flows, because in order for there to be electric work, you need to have a high voltage and a low voltage setup. You need to have a current running through it, but you also need the resistance to actually get work out of the system. And so that resistance can also turn into heat, a heat source. So that's why the resistance in the circuit can actually turn into have some and cause your circuit to heat up. So that's another way to visualize how to use voltage, and hopefully this analogy helps. So in the next video, we'll be starting to deal with other things like, especially as it deals with this resistance, because that's the one that hasn't been defined quite as well. So good luck in your studies, and may the force be with you.